1, 2, 3. Hello? Okay. Can you hear me?
Sounds good.
Okay, thank you. Oh, yes.
Welcome, everyone, to the session on memory systems. I'm Steve Jian from Virginia Tech. I'm the session chair today. For the first talk, we have a speaker from Seoul National University. This is Hwang Yoon Nam. He's a second-year PhD student. He works on DRAM, different aspects of DRAM, reliability, security, processing memory, etc. So let's welcome our speaker.
Hey, hello, my name is Hwang Nam. Today, I'll be talking about our paper, DRAMScope, Uncovering DRAM Microarchitecture and Characteristics by Issuing Memory Commands. This is a collaborative effort between Seoul National University and University of Illinois Urbana-Champaign. Before we begin, let me give you an overview of the paper. We analyzed the structure and error characteristics of DRAM. Through microscopic analysis, we observed the DRAM structure, and through microscopic analysis, we found the bit-flip patterns. First, let's look at the DRAM organization from a macroscopic perspective. DRAM has a hierarchical structure, and each DRAM cells consists of one access transistor and one capacitor. Also, modern chips use an open bin line structure where cells connect to sense amplifiers above or below. However, if you look at this from a microscopic perspective, we can discover new insights. First, let's look at the DRAM organization from a here's the microscopic view of DRAM. Recently, DRAM cells have adopted a 6F square cell structure. If we zoom in, we can see that when the buried water line turns on, it connects the bin line and cell's capacitor. Relative to water line 1, there are water line 0, which is the same P substrate, and water line 2, which is the separate. We call this the neighboring gate and passing gate, respectively. To discover the DRAM structure and characteristics, we use 3 techniques: activating induced bit flips, in-DRAM row copy, and retention time test. Using these techniques, we can test the DRAM chips through non-destructive testing. So the first technique is activating induced bit flips. This happens when activating a row flips the data in adjacent rows. There are 2 attack methods: Rowhammer and row press. Rowhammer involves many short activations, while row press involves fewer but longer activations. The second technique is in-DRAM row copy. Row copy copies data from one row to another row within the same subarray. The process involves activating the source row to write to the sense amplifiers and then copying it to the destination row. The third technique is retention time test. A DRAM cell in charge state loses charge over time. We use this to distinguish between true cells and anti-cells. Here is our experimental setup. We conducted the experiment using DDR4 and HBM2 with FPGA-based infrastructures. We also controlled the DRAM chip's temperature with a temperature controller and logo heaters. We tested lots of DDR4 and HBM2 chips in this paper. First, let's look at the common pitfalls. Before the analysis, let me introduce the common pitfalls of prior works. There are some remapping schemes for address and data. Some of this information is disclosed, but it's easy to overlook. First, the address can be remapped at the RCD chip. Because of the RCD chip, some chips received an address with some bits inverted. Second, the row address can be remapped internally within the chip. Many prior works, including ours, have identified this using single-sided Rowhammer attack. Finally, the DQ pins between a DIMM and each chip are twisted. This is an example showing how the twists occur. Additionally, the data is twisted differently for each chip. So considering these pitfalls, we experimented and analyzed DRAM chips accurately. Let's start with the macroscopic analysis. We conducted multiple macroscopic analysis on DRAM microarchitecture. Here are 3 representative ones: data swizzling and met structure, and coupled row activation, and subarray structure. Data isn't stored sequentially in a DRAM chip. Instead, it's internally swizzled and reorganized. We call this data swizzling and reverse engineered the data swizzling. First, we identified the cell adjacency. The error rate of Rowhammer attack varies with data dependency. So, indicating that cells influence each other not only vertically but also horizontally. In the figure, the yellow cell is the victim cell. We identify the influencing cells by changing the victim row's data. And second, we utilize row copy to distinguish the odd and even bin line. We can figure out if a cell is influenced by upper or lower subarray to determine if a bin line index is odd or even. In short, we identify the data swizzling using Rowhammer and row copy. By using cell adjacency, we can also find the width of the map. Just like there are sense amplifiers between the subarrays, there are Waterline drivers between mats. Therefore, we believe there is no Rowhammer effect between mats. We measured mat widths as 512 bits and 1024 bits. So, inside the DRAM chip, data is remapped by data swizzling, and the mat widths are either 512 bits or 1024 bits. Next, we found the coupled row activation. This is when the two physical row addresses access rows on the same waterline. Normally, only one row corresponding to the input row address is activated. But in a certain by4 and HBM2 chips, we noticed another row being activated as well. So we found the gap between these rows is half of the total rows. For some DRAM chips, activating a row can unintentionally activate its coupled row. So finally, we did a subarray level analysis. Most subarrays are sequentially adjacent following the row address order. However, we found that some subarrays affect each other even if they have a large row address difference, such as quarter of the total rows. These are called edge subarrays, and two edge subarrays work together like a single subarray. So two edge subarrays work in tandem to form a single full subarray. Now let's take a microscopic view of DRAM. Here we introduce two main topics: 6F square induced, activating induced bit flip characteristics, and the adversarial data pattern for first hammer count and bit error rate. First, let's understand the 6F square cell structure a bit more. In a single row, the cells alternate between the top and bottom of the waterline. It means the cells of the single row alternately have a passing gate and neighboring gate relationship with the adjacent waterline. By the way, bit flip mechanisms are different for each gate type. Each gate cross-sections looks like this. So when activating a neighboring gate, electrons gathered by channel inversion are injected into the victim cell, causing a bit flip. On the other hand, in the passing gate, the strong voltage attracts electrons from a victim cell, and then electrons spread out, resulting in a bit flip. We also need to consider whether the waterline index is odd or even. In this figure, you can see the arrangement of cells in a row is identical when both waterline indexes are odd. However, when comparing odd and even indexes, they appear different. So we considered whether the waterline index is even or odd. So here are our attack patterns of activating induced bit flips. We conducted a single-sided Rowhammer and row press attack. This figure represents the average bit error rate when the bit index is modulo 32 for even rows. First, with row press, bit flips were only observed in victim data 1 as reported in the row press paper. Furthermore, in data 1, bit flips occur in both odd and even bits. Unlike row press, Rowhammer causes bit flips both data 0 and 1. However, there is a pattern. In figure E, when the data is 0 and attacked by the upper aggressor row, bit flips occur only in odd bit cells. Conversely, in figure F, when the data is 1 and attacked by upper aggressor, bit flips occur only even cells. If the aggressor is changed from upper to lower, the pattern reverses. So here's the summary of the previous figure. From the row press attack, B-flips occurred only in data 1 and in both gate types. However, from Rowhammer attack, B-flips were observed in both data 0 and 1. But in data 0, B-flips happened only one type of gate, while in data 1, B-flips happened in another type of gate. So we can classify the B-flips patterns not only by data and attack method, but also gate type. And then let's look at the adversarial data pattern in terms of minimum activation count. We found that when the cells surrounding the victim cell have opposite data to the victim cell, the hammer count is lowest. Also, we tested the adversarial data pattern for a bit error rate. The baseline bit error rate is observed when all cells in the victim row are either 0 or 1, and the data in aggressor row is opposite of the victim row's values. We found that the worst case is when the victim and aggressor row have 3, 3, and CC. Data is most vulnerable when it changes by 2 cell spacing, not 1 as previous thought. So when all near cells from the victim cell have opposite values of victim cells, it is most vulnerable. The bit error rate can increase by up to 1.69 times in the worst case data pattern. If you want more details, please refer to our paper. There are a detailed process of reverse engineering 14 observations derived from analysis and new vulnerabilities of activating these B-flips and simple yet effective protection solution. Thank you for listening. If there is any question, please feel free to ask me.
Hi, Kave from ETH Zurich. Nice work. So
thank you.
One question. So I found the discovery that, okay, 2 rows are mapping to the same row inside DRAM, basically, is interesting. So this made it hard to do Rowhammer. Did you try now? Because now this allows you to do double-sided, right? If you basically go a little bit farther to basically sandwich the rows in between, right? So did you try that? And did it work better when you tried?
I tried in terms of In-DRAM TLR. I can do this, but maybe in software, in empty side software mitigation schemes, maybe it is, maybe that schemes not track the couple of rows.
Yes.
Yeah, this is my thought. Thank you.
Thank you.
Stefan Soroyo, Microsoft Research, very nice work. My question is more about, so you presented this data, at least I haven't read the paper. In this talk, you presented, data is like this, data is like that. Is that for one DIM? Is that for DIMs from all the DRAM vendors? Have you seen any changes? Because DRAM vendors use very different technologies when they build the internal topology of the DRAM.
Oh yeah, we tested maybe 3,000 DRAM chips, and also from the 3 main DRAM manufacturers.
Yeah.
Yes, but for HBM2, we just tested only one manufacturer.
But these findings were applied for all the DRAM you tested?
Yes, it is the same.
Wow, okay, thank you.
Thank you.
Are there more questions? I have one question. So in these, so you also did some Rowhammer attack on the DRAM. How many times do you have to activate a row to induce these Rowhammer errors?
Okay. In the graph, we use maybe 300,000 activation count per all the graph. Yes.
I see. It takes about 300 activates to a specific row to cause Rowhammer attacks.
Yeah. Thank you.
All right, for our second talk, our speaker is Aditya Kamath, a PhD student at the University of Washington, working with Professor Simon Peter. He works on analyzing data movement and mitigating its performance impact in contemporary applications. Aditya also used to work on GPUs. Let's welcome our speaker.
Forwards, backwards, and this one is the right that we want to use. Which one's forwards? This one. Okay. This one.
Yeah.
Cool. Thanks. Hey everyone, my name is Aditya K. Kamath, and today I'm presenting MC² lazy MemCopy at the memory controller. So prior work has shown that memory movement consumes a high amount of overhead across many processes. A 2015 paper profiled the behavior of applications in Google's data centers and found that up to 7% of all CPU cycles were consumed by memory movement. In addition, RPC calls and protobuf also had high copy overheads. Another paper profiling Meta's most popular microservices in 2020 saw similar trends with copy overheads of up to 14%. We ourselves conducted a study on several operations across different application domains that exhibited a high copy overhead. And we plotted flame graphs showing the amount of time spent in various functions of these operations, including the memory copy times. So the top two graphs you see depict writes and insertions for OLTP and NoSQL databases. The bottom left graph shows OS copy on write faults, and the bottom right shows common protobuf operations. The bars highlighted in purple show the time spent copying, which can be up to 68% for these operations. Our insights from looking at these applications are that they typically use MemCopy to fill temporary buffers, and this can lead to excessive or redundant copying. When copying happens in the critical path of application processing, it becomes difficult for the CPU to hide its overhead, leading to killer microseconds of copy execution. So to see how these copies are exactly used in modern applications, let's look at a typical use case, specifically read copy updates in multi-version concurrency control databases. So multi-version concurrency control databases, or MVCC databases, copy rows or tuples being modified to local buffers to preserve isolation guarantees. So in this example, we have two threads performing transactions on the database concurrently, and one is a writer and one is a reader. And before performing the modifications, the writer creates a copy of the row that it wishes to modify. The writer then performs its required modifications to its local copy, which allows the reader to read the unmodified data from the original database and avoid inconsistencies in operations. When the writer finally commits the transaction, it merges its row back into the main database, but the entire row may not end up modified, in which case the writer copied more data than it actually needed to. In addition, there's potential for copy overheads to be hidden in the background when other database operations are ongoing. So currently, applications make use of what we call eager copying, where a copy operation causes data to be moved. Then on access, the required data is obtained from the destination location. But for the applications we previously saw, we find that this is not the best approach for data movement, and instead we propose performing the data movement lazily. So on a copy operation, as the name suggests, we don't do anything, we're lazy. When the data is finally accessed, we reroute the request to the appropriate location and perform the data copy in place. And this method allows only the data that is accessed to be copied, and it allows the hardware prefetcher to trigger copies before the data is actually accessed to hide copy latencies. So to support this operation, we propose MC², performing lazy MemCopy at the memory controller. And we find that the memory controller is the best place to handle all of this, as all the memory accesses must pass through it, and it frees up responsibilities from the CPU and provides opportunities for copy hiding. The system has three main components: hardware modifications to the memory controller, two new instructions, and a software wrapper. And we'll look at each of these in depth. So we add what we call a copy tracking table, or CTT, which tracks all the prospective copies. Each entry in this table has a 52-bit destination address, a 52-bit source address, and a 21-bit size of executed copies, along with an active bit to check whether the entry is actually in use. We use 52 bits for addresses, since this is typically the size of physical addresses in systems today. The 21-bit size allows us to track a prospective copy of up to 2 MB, or the size of a large page. The entries in the CTT are kept coherent across the memory controller, and the CTT is looked up in parallel with memory access, so its access latency is hidden in the critical path. We also maintain a bounce pending queue that temporarily holds writes to source buffers for consistency. The importance of the bounce pending queue is explained in the paper. We won't get into too much detail here. So we provide two new instructions to take advantage of MC squared. The first is MC lazy, which is what initiates the lazy MemCopy operation. It accepts three registers: the destination virtual address, the source virtual address, and the copy size. The second instruction is MC free, which is a hint to the system that informs it that the address is no longer in use and does not need to be tracked anymore. So MC lazy has a few alignment restrictions to simplify the hardware. We provide software wrappers that hide these constraints from the programmer. The first requirement is that the destination buffer address must be cache line aligned. This is because memory accesses occur at a cache line granularity, and lazy copies on partial cache lines would make the hardware very complicated. The second restriction is that the copy size must be a multiple of the cache line size for the same reason of avoiding partial cache line copies. And the final restriction is that the destination and source buffers must be contiguous in physical memory. For user space applications, this means that they must each individually lie within a single page. And for copies spanning multiple pages, you basically call MC lazy individually on each page. But you don't have to worry about this. We provide a C wrapper around MC lazy called MemCopy lazy, which has identical semantics to the libc MemCopy you may be familiar with, and it hides all of these low-level details from the programmer. So we'll now look at how the actual lazy copy operation is performed and what happens on memory access. So first, let's assume that the CPU core executes an MC lazy operation on a destination and source cache line. So the CPU will create a packet for this operation and send it towards the caches. At the caches, the operation triggers an effect where the destination is invalidated and the source is written back. And this ensures that further access to the destination end up going to the memory, and the memory has the up-to-date values of the source that was supposed to be copied to the destination. The packet is then broadcasted to all the memory controllers where the operation is added to the copy tracking table. And now we'll look at how reads to the destination buffer are impacted by the operation. So when the CPU reads the destination, we need to obtain the correct data from the source since the data wasn't actually copied. So the access first proceeds as normal. At the memory controller, we consult the CTT and realize this was actually the destination of a prospective copy. This causes the request to be bounced to the memory controller containing the source cache line. The source cache line is then read from memory and sent to the CPU core as if it was read from the destination memory location. Reads to the destination incur an additional latency due to the CTT lookup and bounce operations. In our paper, we also detail out how the reads to source and writes to source at destination are also performed. So there are a few questions we want to answer in our evaluation, namely, how much lower is MC Square's copy overhead? What impact does it have on access latencies, and what benefit does it provide real workloads? In our full paper, we answer a few more questions which we won't be able to cover here. But to answer these questions, we make use of Gem5, a cycle levels CPU simulator, and we simulate a configuration that is supposed to model a scaled down CPU server node with 8 CPUs. So wherever possible, we compare against Xeo, which is a state-of-the-art OS-based copy on access mechanism, which makes use of OS-managed page tables to align copies. Xeo is essentially the OS-based approach to lazy copying, but it requires expensive page table management operations, and it has high access penalties because of page faults. So to evaluate the latency of copying, we performed an experiment where different size source buffers were copied to destination buffers, and just note that the y-axis is in log scale. So we evaluate against MemCopy in two scenarios. The first is where none of the data is cached, referred to as just MemCopy. And the second is where the source and destination buffers have just been accessed before the copy is performed, allowing them to be cached, which we call touched MemCopy. And these are essentially the best and worst case performance for MemCopy. Copies with high overhead typically perform near the uncached MemCopy because of memory access latencies. So MC Square provides speedups for copies at and above 1 KB, performing similar to copying cached data at 64 KB and above, and it's up to 11 times faster than uncached MemCopy. Since Xeo relies on page table manipulation, it only ran for copies at and above a 16 KB size. It has a high initial overhead due to page table manipulation and TLB shootdowns. Below 256 KB, MC Squared outperforms Xeo. Above this, Xeo outperforms MC Square, as MC Square has that cache line flushing, which has its own overhead. But despite this, we see that MC Square still provides benefits at these sizes, and we'll see why exactly. So to analyze the impact of lazily copying on access latencies, we ran a micro benchmark where 4 MB source buffer is copied to destination buffer. the destination is then accessed sequentially. And we intentionally misaligned the source and destination, as in the applications we examined, this is typical. And MC² suffers a slight penalty when they're misaligned. So we gave ourselves the worst performance in this evaluation. So the runtime of each system is normalized to the time taken by MemCopy, which is the flat black line. And higher means slower. We analyze the runtime when different percentages of the 4 MB buffer are accessed. And as we previously saw, Zio outperforms MC² when the data set isn't accessed. But once we start accessing the destination buffer, Zio starts seeing page faults, and that triggers copies, giving it overhead. When more than 25% of the data set is accessed, it actually performs worse than MemCopy. On the other hand, MC² is able to retain low access penalties no matter how much you access. Surprisingly, even when the entire data set is accessed, MC² outperforms MemCopy. And this is because the cache prefetcher hides some of the extra access latencies. When we turn off the prefetcher, we see that it does slow down compared to MemCopy, showing the impact of copy latency hiding by the hardware prefetcher. And when the source and destination buffer are aligned, we see even better performance. So moving on to the performance of applications with MC², we see that many database transactions involve updating only small portions of a tuple. For example, in the TPCC workload, when you decrement the quantity of a stock of an item being sold in the store, only 1 to 2% of the actual tuple ends up being modified. And as we previously saw, this leads to excessive data being copied because of read-copy updates performed by MVCC databases. So with MC², we could pay the copy overheads only for the amount of data which is being updated. And to evaluate this, we enhanced Cicada database, which is an MVCC database, with MC², and performed repeated operations on a table with 8 KB sized rows, modifying different fractions of the tuple and measuring throughput. So these operations are split 50-50 between reads and updates, which are typical of write-intensive database workloads, and we use 8 threads to saturate all the cores on our system. So MC² is able to provide 78% higher throughput for 6% update fraction. And this is because it reduces the memory bandwidth consumed for the smaller update fractions. We also analyze MC² with protobuf workload provided in Google's Fleetbench benchmark suite. So Fleetbench contains workloads dedicated to common hot library functions constructed from traces using from production servers. And we find that MC² here has a 43% lower runtime compared to MemCopy. Zio isn't able to generate any performance benefits since all the copies in this benchmark were smaller than 4 KB, which is the size of a page. We also replicated an experiment from the Zio paper where MongoDB insertions are performed using 100 KB fields and 10 fields per insertion. Here, MC² provided an average 15% lower latency for insertion, while Zio actually slowed down by 9%. This is because the copied data ends up being later accessed, triggering page faults for Zio, which MC² avoids. So to summarize, we introduced MC², a novel lazy copy mechanism at the memory controller. It provides up to 11x faster copying than standard MemCopy, and it provides benefits across workloads such as protobuf, MongoDB, MVCC. We also analyze some Linux kernel copying in our paper. Our code is completely open source on GitHub, and thank you for attending this talk.
Very nice piece of work. I was wondering, so I had a question about, have you, you're copying, you preserve the semantic, like in other words, you have a library in the software, and if I go through your library, you do all this stuff for me. But have you thought about, and that's fine, have you thought about making restrictions as to what I can do with the data that I lazy copy so that it makes your problem easier? Like for example, I want to copy and then you're going to copy it lazily for me, but I can't write to it until you give me a thumb up that I can start writing, or the data is read-only for something like that. Have you thought about changing the semantics of the copy operation in software to make the hardware implementation simpler, easier, better?
That's it. Great. Yeah. Do you have a follow-up? Sorry.
Have you, like my question, it's fine that you haven't done it, have you considered it?
So that's a great question. When we were coming up with the design, we were trying to consider different options. So one thing is we didn't want to change the software too much for the programmer because that ends up, if you have to redesign your software, it becomes, And I didn't mention this, but we provide like a library interposer, which allows you to convert all the MemCopies to lazy MemCopies in your application. So a big part of what we wanted is just minimize the amount of code changes you need to do to adopt this. And like, if you could keep the exact same application, that would be great.
Yeah.
But I do believe what you say, if you do add these restrictions, you could simplify hardware, possibly get even better performance.
Okay,
But
thank
it was
you.
a trade-off we didn't want to.
Yeah. Thank you.
Great question.
Actually, this is jumping down from Purdue. I have quite similar questions because it seems like you don't do the MemCopy on time, you just delay that until the data is accessed. What if this is not data accessed? So when is the time you just do the MemCopy?
Yeah, so our copy tracking table is limited. It has like 2,000 entries, 2048 entries. So once we start seeing the table filling up, we'll start copying in the background and start eliminating the entries. That's one of the ways we do like copy latency hiding is just by copying stuff in the background. So even if it doesn't get accessed, eventually it might get removed from the table by copying in the background.
Okay. So what if during the background searching of that table, what if the buffer happens? So because if there's no such technique, after execution of the memory copy functions, the programmers expected that the memory system becomes consistent after that function call. But in your design, there's no such guarantee.
So yeah, in our paper, we actually have a section on data consistency. That was like a big part of this system design is how do we preserve data consistency despite like different operations happening in parallel. It's a bit complicated, but the bounce pending queue and all of that is to support that, to make sure that while stuff is being copied and other stuff is being accessed, there's no interference happening. I would redirect you to the paper. We do go over that in the
Okay,
paper.
yeah, thank you.
But great question. Thank you for asking.
Let's thank the speaker again. All right, our next speaker is Yesen Ru. She's a principal engineer with the DRAM design team at Samsung Electronics. She has contributed to a lot of DRAM technologies, including LPDDR4, DDR5, HBM 2 and 3. Currently, she is studying at Songkyun Kwon University while still working at Samsung. Her current research interests include memory RAS features, especially for on-die ECC, 3D DRAM, and DRAM cache. Let's give our attention to the speaker.
Hello everyone, my name is Yeshin. During my DRAM development career, I noticed the ongoing effort in the industry to use DRAM as a cache, which prompted me to explore what a cache-optimized DRAM would look like and how its controller could be designed. This led to this paper that I will be discussing today. So I hope this presentation will spark a meaningful discussion. As the demand for data processing continues to rise, the number of CPU cores data center is growing rapidly. Looking to the future, the International Roadmap for Devices and Systems predicts that by 2034, CPU could have up to 640 cores. However, as shown by the red line graph, the increase in core count must be matched by an expansion in last-level cache size. Without this, both performance and energy efficiency could suffer. Typically, each socket requires 1 to 4 GB of LLC. To efficiently integrate large caches, CPU manufacturers have adopted a new approach called heterogeneous integration. Examples of this include AMD's Vcache and Intel Sapphire Rapids with HBM2E stack. The main difference between these two approaches lies in the structure of SRAM and DRAM. As shown, SRAM consists of 6 transistors to store 1 bit, whereas DRAM has simple structure with 1 transistor and 1 capacitor. Considering the increasing number of cores, this makes DRAM more advantageous in terms of density and scalability. However, there are challenges to overcome when using DRAM as a cache at both circuit and architecture levels. In a set associative cache setup, serialized accesses are needed before a data request to read tag and leading to significant latency increase and reduced cache throughput. Although it's possible to fetch tag and data simultaneously, this capability is limited to direct mapped cache only. Moreover, because tag must be read before a write operation, the sequential accesses cannot be entirely avoided. Additionally, DRAM introduces inherent delays as it needs to activate a specific row before issuing read or write commands. Sometimes these architectural overheads overweigh circuit level overheads. So I would like to introduce native DRAM cache, a new type of DRAM cache designed for processing in memory. This is the NDC overview. We propose caching in memory, allowing cache operations to be processed within DRAM itself by autonomously performing functions such as tag matching, way selection, and cache replacement within DRAM. It can eliminate the architectural overheads. Thus, a memory controller can manage these operations with a simple command sequence as shown in the timing diagram. An important aspect is that this caching in memory scheme operates within a subarray of DRAM, which is a group of rows that share a row buffer. Typically, adding circuits within subarray imposes significant area overhead on DRAM. However, NDC limits this overhead to just 0.6% through microarchitecture changes in the subarray area. As a result, NDC demonstrates significant performance improvements in spec MPB gap benchmarks 2.8, 52.5, and 44.2% respectively. The next slide will delve deeper into native DRAM cache and its three features. The first feature is in subarray processing. Allow me to briefly explain the structure of DRAM. Each subarray is composed of multiple mats, and bitline sensor performs the function of sensing bitline and bitline bar in a mat, also serving as a device to store data from an activated row. Hence, it is also called row buffer. In DRAM cache, the activated row corresponds to a set selected by an index. On the other hand, DRAM caches typically store metadata such as tag, value status, dirty status, etc., along with data by adding dedicated mats. In NDC, we redesigned the microarchitecture of the metadata mats to implement cache operations. Now, let's take a look at the tag matching circuit in NDC. The circuit on the left represents the traditional mat used in DRAM. The tag matching circuit motivated by CAM with 3 transistor matching is configured as shown on the right to compare the data stored in bitline sense amp with the tag line and output these to the match line. This circuit allows simultaneously matching of all data sensed by bitline sense amp, making it straightforward to manage a large number of ways. For example, in two-way set associative cache configuration, if a hit occurs in way 1, the match line of way 1 stays at 1, enabling read or write operation to the corresponding data area. This in subarray processing enables single-access cache control. The following slides will demonstrate how each cache operation is facilitated using NDC. During activation, data from row selected by an index is stored in a row buffer. Then tag is inputted with a read command, and the mat for metadata determines the hit status. Subsequently, if there is a way where a hit occurred, data from that way is read. Additionally, the hit is reported to the controller through a dedicated pin. This reporting is crucial for a controller to ascertain whether it is a hit or a miss and to schedule subsequent operations accordingly. On the contrary, when examining a miss, since there is no hit in any way, the data does not need to be read out. This is more efficient and leads to better throughput and energy savings than traditional DRAM caches, which often transfer unnecessary missed data. Here, it's clear that the write-hit case is similar to the read-hit case. Now, suppose there is a write miss, then NDC must arbitrarily determine the victim way to write the new data. If a clean way is present, NDC can easily determine the victim way and write the new data on that way. In the case of dirty miss, a slightly more involved operation is required. The data from the randomly selected victim way is moved to the victim buffer, then the new data can be written on the victim way. This process is similar to the traditional DRAM read, modify, write operation and can be described as a read, store, write operation. Now, I will explain the final feature of NDC, which is the address mapping strategy. Generally, when there is a likelihood of accessing consecutive addresses in address space sequentially, placing them in different sets, as shown in the left option 1, can improve the cache hit ratio. However, each set corresponds to a different row in a DRAM cache, thereby potentially reducing the row buffer hit ratio. On the other hand, placing them in the same set as depicted in the right option 2 can enhance the row buffer hit ratio. However, that being the case, the cache hit ratio can be degraded due to cache conflicts. This illustrates the address mapping dilemma in DRAM caches highlighted in the prior work. By contrast, leveraging NDC's capability to easily increase the number of ways allows placing the consecutive addresses into different ways within the same set to avoid the conflicts. This improves the row buffer hit ratio without degrading the cache hit ratio. As a result of these three features, NDC can achieve a high cache hit ratio by providing high level of associativity similar to set associative cache setup like LH cache, plus its single access control much like direct mapped cache models such as alloy cache enables achieving high throughput. Now I will break down the experimental results. We used HSpice to measure the delay caused by tag matching and way selection in NDC. Under these conditions, a 16-way NDC incurs an additional 1.09 nanoseconds of latency compared to conventional DRAM. Taking into account this latency increase, we compared the performance of a system with NDC to that of other cache models. Owing to its high cache hit ratio and high row buffer hit ratio, and this is performance improvement compared to the state-of-the-art in spec MPB gap benchmarks is 2.8, 52.5, and 44.2% respectively. Furthermore, reducing unnecessary data transfers and simplifying the interface results in energy savings of 17.7, 25.8, and 34.6%. In conclusion, NDC leverages an innovative DRAM microarchitecture to provide caching in memory. We have demonstrated the performance improvements and energy savings of NDC, positioning it as a highly promising solution for data centers facing increasing core counts. Thank you for listening.
Hi, this is Baek from Samsung SDS, and I have about 2 questions. First one is, did you ever consider the cache coherency protocol such as the MOSI or MESI protocol to implement into your DRAM LLC cache, because the last level cache must support a cache coherency protocol in CPU. So did you ever, and the other one is, did you ever consider about the Rowhammer side channel attack on the DRAM LLC cache, because there's these Rowhammer that can disintegrate the data integrity on the cache level? Thank you.
Thank you for your question. When it comes to cache coherency, it is the last level cache and just placed just in front of the main memory. So we assume that everything is done before the memory controller of that cache. So L1 and L2 cache, we set the experimental environment, having L1 and L2 is private cache and L3 is shared cache, the process that you mentioned is done before the disk cache processing.
The address is the L4 one? Okay.
Okay. And second question is about Rowhammer. I think that is very great question because cache memory tend to be accessed very, specific address, but actually that is our future work.
Thank you very much.
Hi, Moin Qureshi, Georgia Tech. A quick question. You said that Alloy cache has low row buffer hit rate. I was a little bit confused because Alloy cache is a direct map cache. If you're streaming, then consecutive lines will go to consecutive sets. They will all be in the same row buffer. Why do you get low row buffer hit rate for Alloy cache?
Okay. Actually, I don't think Alloy cache has low buffer hit ratio, but it depends on the memory mapping, address mapping. If you place the consecutive address in the different row, it could reduce the row buffer hit ratio. But if you place the consecutive address in the same row, then it's row buffer hit ratio can be stay its level. So okay.
Okay, thank you. No, I know. There is one more.
Yeah.
Hello, Shai from Google. Memory bandwidth is a big issue with high core count servers. How does increasing cache on a resource which is already highly contended help the system?
Sorry, could you come again?
The memory bandwidth is already highly contended. How does increasing the cache by increasing that cache on the other side of the memory bandwidth sidewall help the system?
You mean the memory bandwidth is already high, sufficient? So it could be, but we find that there is still workload that is memory intensive work, need to high capacity and high bandwidth memory. So I think caching in memory strategy can help to improve the limit of memory bandwidth.
Okay, thanks.
All right, for our last talk of this session, our speaker is Hammer Jaleel, a principal research scientist at NVIDIA Research. His current focus is on memory systems, heterogeneous architectures, and workload characterization.
Can everybody hear me? Yes. Okay. Thank you for the introduction. This work is done in collaboration with Guraj, Steve, and Moin. So Rowhammer is a security problem that has been troubling the DRAM industry for a little over a decade now. State-of-the-art secure solutions to address Rowhammer incur a large amount of storage overhead. To address this, industry deployed low overhead trackers within DRAM, but unfortunately these low overhead trackers were defeated because they are address pattern independent. So until now, all hope has been lost for low cost in DRAM trackers. Today I will show you that it is possible to design a principled access pattern independent in-DRAM tracker that will be secure to Rowhammer mitigation, and it only costs 4 entries within the tracker. So what exactly is Rowhammer? Well, Rowhammer is a phenomenon where frequent accesses to DRAM rows, called aggressor rows, cause bit flips in victim rows that are physically adjacent to it. The Rowhammer threshold, which is the number of activations required to flip bits, is reducing with each generation. With current trends, Rowhammer is not just a security problem, but it is also a reliability problem, and we desire a low-cost and scalable solution to address Rowhammer. So Rowhammer solutions can either be deployed in the memory controller or within DRAM. We will focus on in-DRAM solutions. There are two parts to addressing Rowhammer. First, you need a structure to track the aggressor rows. Second, we need to mitigate the victims of the aggressor rows. To better understand how victim mitigation is done, let's take a crash course in DRAM refresh. So DRAM refresh period is divided into 8,000 refresh intervals. And each of these refresh intervals has a timing of roughly Tref I. A small fraction of the rows at the end of each Tref interval is what we call Tref C, or refresh. And in this refresh period, a small number of rows are refreshed. This allows the remainder of the Tref E to actually perform DRAM operations. For our DRAM parameters, you can actually have at most 79 activates that you can process at a time. It is during this TRFC window that DRAM buys some time to go about mitigating the victim rows by consulting your tracker, identifying which entry from within the tracker to take, and mitigate the associated victims for Rowhammer. So now that we understand refresh, let us look at the landscape of in-DRAM Rowhammer solutions. First, we have secure in-DRAM mitigations such as ProTRR and Mithril. These require thousands of counters per DRAM bank. And as the Rowhammer threshold decreases, the storage overhead for these techniques increases. On the other hand, we have the DRAM vendor solutions like TRR, DSAC, and PAT. These require only a handful of counters. Unfortunately, attacks such as Trespass and Blacksmith, which exploited the access pattern dependency of these trackers, they defeated such trackers. Our goal is to maintain the low cost of existing in-DRAM trackers, but provide high security. Okay, to understand why existing low-cost trackers fail, let's first quickly look at tracker management policies and their associated failures. You have a tracker, you need to insert something into it. You decide whether or not you want to insert something into it. When the tracker is full, you need to find a suitable victim to evict. When it comes to mitigation time, when you're at refresh, you need to choose an entry from within the tracker to decide to mitigate. Each of these three policies has an associated failure mode. Should you choose not to insert an entry within the tracker, you will suffer from a tracker insertion failure. Depending on your eviction policy, if you choose to evict a victim, an address from the tracker, that victim may not get mitigated. As such, these failures are called tracker retention failures. Since, as you saw from refresh, the victims are mitigated at the time of refresh, the delay in issuing a mitigation after inserting into the tracker is called tardiness. Okay? So, using these modes in mind, why do existing low-cost trackers fail? Existing low-cost trackers are counter-based that use frequency information to decide what to evict and frequency information to decide what to mitigate. Since frequency information is access pattern dependent, attacks like Trespass and Blacksmith were carefully crafted to bypass these mitigations, to render these trackers insecure. So our goal is to design an access pattern independent tracker that has bounded failure rate. Since we know that counters are one of the reasons for the insecurity in existing trackers, let's design a tracker that requires no counters. Let's just remove them. So now if you have a tracker that is just holding addresses, how do you go about managing such a tracker? We propose to use FIFO management. Recall, with the FIFO, you can never do random access in. You can either fill or you can actually read out. So
FIFO gives us a way to bound the tracker failure modes, as we will see later. So how is a FIFO tracker managed? We will always insert activations into the FIFO. And we're not, since the FIFO does not allow you random access, we're always going to insert. Even if the entries, even if an address is within the tracker, we will still insert. This allows the tracker management to be independent of accesses that are before or after. The eviction policy and the mitigation policy will use FIFO management as well. So if the tracker is full, take the first entry out. If the mitigation, when you want to mitigate, take the oldest entry out. If you just use a FIFO tracker, unfortunately, this is not access pattern independent, because if you design an access pattern that is larger than the FIFO size, you're going to constantly have retention failures. So to avoid this, we're going to propose a probabilistic insertion policy. Now, when we're assuming this insertion policy, it is probabilistic, it's not, and we need to now identify what is the best sampling rate for our insertion policy. So to do this, let's go back and recall from our crash course on DRAM, refresh, that refresh was happening, the Rowhammer mitigation was happening during the TRFC window. We were showing one mitigation. And during a given TRFC window, you can have up to 79 activates. So our mitigation rate is roughly 1 over 79, once every 79 activations. So if we use the continuity principle, right, what we need to ensure is that our insertion rate must match the mitigation rate. So the sampling probability that we should use is P equals to 1 over 79. So there you have it. That's PRIDE. This is a In-DRAM tracker that should be secured to roll against any arbitrary access pattern. So let's go about trying to bound the failure rate of PRIDE. So recall, the first failure is due to insertion. Since PRIDE chooses something with probability P to insert, right, we can bound the failure rate for insertion by computing the probability of not inserting, and if we want to know that if it's going to cause a Rowhammer, if it's going to cause it's going to violate the Rowhammer threshold, we would say we would take the probability and raise it to TRH, and that would be our failure rate. For a failure rate of 10,000 years, this the tracker insertion failure can be bounded by a TRH of 1530. Okay, let's talk about TRF now. So how do you go about computing the tracker retention failure? So the tracker retention failure can be modeled as follows. The FIFO can be thought of as a lossy buffer that has a loss probability L. So if you're going to lose something with probability L from the tracker, you're going to survive in the tracker with probability of 1 minus L. So the effective sampling probability is P equals to P hat is equals to P times 1 minus L. So using the same way that we can compute the failure rate for the tracker, it would now be 1 minus P hat raised to TRH. So this formula now is depending on the loss probability. So how do you go about computing the loss probability of the tracker? So it turns out that the loss probability is dependent on the position of an aggressor row within the refresh interval. There are 79 possible positions within the refresh interval. And if you decide to insert at the very beginning of the refresh interval, you will have a higher loss probability. If you decide to insert it towards the tail end of the refresh interval, you would have a low loss probability. Since we want our tracker to be access pattern independent, we'll use the worst case loss probability for a given tracker size. We use Monte Carlo simulations and analytical models to compute the loss probability. I'm not going to go into details over there, but if we had a 16-entry FIFO, the loss probability is 0.03. So now what you can do is you can take the loss probability, you can take the probability of insertion, assuming again that we have a failure rate of 10,000 years. For a 16-entry FIFO, we can now tolerate a Rowhammer threshold of 1575. Okay, so now the last thing that's left is computing tardiness. So recall, that the In-DRAM tracker delays mitigation until the refresh period. If you have a refresh interval with W possible activations in a one-entry buffer, then the buffered aggressor row can be accessed W times before it is mitigated. Thus, the tardiness is W. Generalizing this, if you have an N-entry FIFO, the tardiness for the newly buffered aggressor row is N times W. So, and as the tracker size increases, the tardiness also ends up increasing. This chart shows the effective Rowhammer threshold of pride with and without tardiness. What you end up seeing is that if you don't include tardiness, as you increase the buffer size, your tolerated Rowhammer threshold ends up decreasing. But once you take into account tardiness, if you have a larger buffer, tardiness causes your effective Rowhammer threshold to increase. If you have a smaller buffer, the retention failures causes your Rowhammer threshold to increase. So there's a sweet spot between a large buffer and a small buffer. So what we're showcasing over here is that large buffers are not always useful because of tardiness. A 4-entry buffer performs best, and it gives you a Rowhammer threshold of 1900. So in our baseline scenario, since pride actually incurs 0% overhead because the refreshes are, the mitigation is issued during TRFC. So in a baseline scenario, we can tolerate a Rowhammer threshold of 1900 with 0% performance loss. We can actually go by scaling the Rowhammer to lower Rowhammer thresholds by increasing the frequency of mitigation. Rather than issuing a mitigation once every 79 activates, we can issue a mitigation once every 16 activates, for example. If we decided to do that, the trade-off is in terms of performance because we can use DRAM's RFM commands to issue a mitigation periodically. We can scale the Rowhammer threshold down to 400, but the overhead is roughly 1.6%. So, in conclusion, Rowhammer is a security and reliability problem. Existing low-cost in-DRAM trackers are insecure. Until now, the inability of DRAM vendors to design secure low-cost in-DRAM trackers, they have decided to move towards more complex storage-heavy solutions such as per-row access counters. However, we're showing that it is actually possible to design a low-cost in-DRAM tracker if we use a principled approach to tracker design. Pride is the first secure low-cost in-DRAM tracker that can address not only the TRH of today, Rowhammer thresholds of today, but we can actually scale it to the thresholds of tomorrow. There are a bunch of other contributions within the paper, which I don't have time to go over to. With that, I'll be happy to take any questions.
Michael James came from SNU South Korea. I really loved your structured approach, and the question I had is the performance overhead? I know that power can be like in-DRAM or interface compatible, but is the performance overhead similar to Para with the Pride?
So Para can actually be employed within the memory controller by using DDR's DRFM command, right? So DRFM has some limitations as defined by the spec, but even if we do exclude those limitations, we actually, the cost of a DRFM is larger than the cost of an RFM. So in general, what we have seen is that Pride actually performs better than using DRFM to implement Para.
Thank you.
Stefan Saray from Microsoft Research. Clear talk, I loved it. That was great.
Thank you.
So my question, so your MTTF on the slides was 10,000 years for the formula. So if I'm worried about the security of a system that has hundreds of DRAM devices or hundreds of servers, and I want to do an MTTF system-wide,
yes,
that's 10,000 years. Do I use the same math, or should I start?
You would use the same math.
Yes.
Yes, and but you would now take into account
the independent failures across.
The independent failures,
okay.
yes. And we have, the math is in the paper.
Oh, okay.
And we've actually evaluated across larger system failures as well.
But because the failures are independent, I have to take that into account, and the thresholds will increase at that point. Is that fair to assume or no, if I want to have an MTTF of 10,000?
Would the MTTF, would the failures, would the Rowhammer threshold increase?
The one that I can tolerate. If I want to have a 10,000 MTTF across my entire system,
Yes.
well, then so you told me that you can support thresholds up to, I don't know,
Yes.
1,700 or whatever that number was.
Let me see. I don't have it in the paper, but I don't have it in the slide deck, but the paper provides sensitivity
Thank
to
you.
larger MTTFs.
Karthik Swaminathan, IBM Research. So in addition to Rowhammer, there was also this phenomenon, I think, called row press, which talked about leaving an aggressor row on for a long period of time and causing flips. Is this something that can be addressed with this approach as well? Like just probably instead of just the number of instead just the number, also look at like some temporal behavior.
As it is right now, we're not tolerating row press with it.
Okay.
But one can imagine trying to figure out how we can scale what the damage of row press is and scale it to how you insert something into the tracker.
Yeah.
We haven't evaluated it as part of this paper.
Sure.
It's part of ongoing work.
But would that also be better to be done in DRAM? Because I think row press proposed in memory controller solution. So would you propose that would also be done in DRAM like Pride?
I think the philosophy is if it's a DRAM vendor problem, don't put it on the system vendors on the compute system to take care of it. If you solve it in the DRAM vendor, it avoids a fragmented solution. Nobody else has to worry about it. So yes, it would be great if we could just do it within the DRAM itself.
Sounds good. All right, thank you.
Thank you.
All right, this is the end of the memory session. Welcome to the talks, and if you have more questions, please talk to the speakers at the poster session.